So our next speaker today is a former Kataev student who's now a professor of computer science at the University of Chicago, where they've worked extensively on topics in quantum complexity, quantum algorithms, cryptography, and quantum computing. So today, Bill Fefferman will now speak to us about a rather timely topic, which is the power of random quantum circuits. So it's all yours, Bill.
All right, thanks a lot. Ryan, let me just make sure. Do people hear what I'm saying? Okay, awesome. I'm going to share my screen. And then, let's see. I think I'm going to stop my video if that's okay. I think it's sort of my bandwidth is limited, unfortunately. Okay, so now let me start. Oops, wait, hold on. Okay, good. So we also see my slides? We do, right?
Yes, very good.
All right, wonderful. So, okay, so I'm going to talk about the power of random quantum circuits. You know, I want to talk about this topic from sort of two perspectives, and I think they're complementary, and it's very interesting to see them sort of interplay with each other. The one is a perspective of hardness, and this is joint with Adam Bolin, Chinmay Nurki, and Umesh Vazirani. And then the second is an easiness perspective. It's very new work, sort of numerical work with Kyungju No and Liang Jiang at U Chicago. Okay, so the starting point of this talk, as we know, we've sort of arrived at this very exciting era in which existing quantum experiments can solve problems that seem challenging for classical computers. What this means, you know, is that experiments are now large enough so that the best known classical simulation techniques take a large amount of time on classical supercomputers. But at the same time, these experiments have, you know, important limitations which could potentially be exploited by faster classical algorithms, right? So for example, they have restricted depth or uncorrected noise. And, you know, from the perspective of, you know, a classical simulation algorithm, this is sort of adding structure to the simulation problem. And we want to be sure that we're sort of not inadvertently adding too much structure. And we don't have unexpected algorithms for simulating these problems. All right, so of course, the first goal for this near-term era is what we call quantum supremacy. And this has been the topic of the last 2 days. It needs no introduction by itself. But, you know, I will say that when you try to define what this actually means, it's a bit subtle, right? I think notoriously so. So let me try to say what I think it should mean. I think we should try to find a task that simultaneously can be solved experimentally on near-term hardware, but also is classically hard. And I think this is the tricky part. You know, I think this should mean both that there's good theoretical or asymptotic hardness evidence from complexity theory that, you know, as the size of the system scales, there's no polynomial and n-time algorithm that solves this problem. So that's generally what we mean by hardness as a complexity theorist. But, you know, we also want, you know, something a little bit more pragmatic, which is that at the end of the day, we're implementing this, and, you know, the experiment is implementing this for some fixed system size. And so we want to be sure that we can't solve this problem in a comparable amount of time by a classical supercomputer, right? So of course, these two things are related to each other, but I think they're somewhat different. And then, of course, we want a procedure for verification, right? We need to be sure that we're solving the problem correctly. Okay. Great. So what is, oh, okay, so we already have a question, is that right? Oh no, okay, fine. All right, so what is Google's approach? So they have this random circuit sampling proposal, which you've already heard about in Sergio's talk and in many of the talks. You know, which from my perspective is the following. This is admittedly a bit idealized. We want to generate a quantum circuit on a 2D lattice with, let's say, square root n layers of Haar random nearest neighbor gates. Right. So if you look at my picture, this is sort of how a theorist thinks about, you know, quantum experiment. The dots here are qubits. The edges are, you know, 2-qubit Haar random nearest neighbor gates. And you know, this is a single layer, but of course, in reality, we can have you know, a square root n number of different layers. So the next layer, for example, the gates could act on horizontal neighbors instead of vertical neighbors, right? So they could all be different. And then we start in the all zero input state. We apply a random quantum circuit with square root n of these layers, and we measure in the computational basis, and that's our sampling problem. Okay, so we're sampling from the output distribution of this random quantum circuit. Great. So from the perspective of quantum supremacy, why are random circuits an attractive proposal, right? Why might Google have chosen to do this? Well, I think there's many reasons. First of all, of course, it's experimentally feasible. And I think from a theoretical perspective, this is sort of wrapped up with the fact that we're reasonably optimistic that this problem is hard at comparatively low depth and system size. Okay, we won't be too specific about this at this point, but this is important, right? And then I think also there are important advantages for verification and benchmarking of random circuits. And most of these come from the fact that the output distribution of random circuits have what we call the Porter-Thomas property, which is essentially saying if you fix an outcome X, then the probability over the choice of random circuit that the probability of that outcome occurring after measurement, is equal to Q over N is exponentially distributed in Q. Okay, so that's the Porter-Thomas property, and we can use this property to calculate the ideal score of a random circuit on benchmarking tests. So in a nutshell, this is how Google understands what their ideal cross-entropy score should be. Right? It comes from this Porter-Thomas property, which then itself is inherited from the random quantum circuit. Okay, so that's great. That's why random circuits are sort of appealing in the near term. But of course, as complexity theorists, what we want to know is deeper. Why should this be a hard task? I think again, from a high level, in the last maybe 10 or so years, we have, as a community, have given good evidence that this random circuit sampling problem is classically hard, at least in the noiseless case. Okay, and this is not at all obvious. I mean, if you think about it, prior quantum algorithms don't look anything like a random circuit necessarily, right? And so even in the noiseless case, this is an interesting problem. And so starting with this paper that, I think, again, it was way ahead of its time. It's like 6 years before anyone else thought about this idea again, really, of Turhal, DiVincenzo. And then this later paper by Bremner, Joza, and Shepard, what they're doing essentially is, in my language, establishing worst case hardness of sampling results. So what they're saying, roughly speaking, is that there's some restrictive class of circuits with the property that if there was a classical algorithm that could sample from the output distribution of all of those circuits, then the polynomial time hierarchy would collapse. Okay, so there's good hardness evidence that this is not the case. Okay, then there's this famous paper by Aronson and Arkhipov. From my perspective, this is the first paper that really considered random quantum circuits, but they were considering it in a very special setting, this boson sampling setting, where these random circuits had very special properties. Okay, they came from linear optics, and there was a connection to the permanent and so on. Then there's Aronson and Chen. This is talking about the hardness of scoring well on a benchmark test, like cross entropy or the Hogg test. And then we'll talk about this next paper very shortly. Okay. Now, what I want to say, though, is these were really, I think, fundamentally in the sort of noiseless case. And it's possible that these arguments will carry over to the noisy case. But I think it's fair to say that we're less certain about this. It generally requires sort of non-standard hardness conjectures that I think may well be true, and we can try to give evidence for them. But again, I think it's fair to say that the community is not really, is not totally familiar with these hardness arguments, and it's not something like P equal NP or something that we at least have a lot of experience dealing with. Okay, so what are we going to do today? Well, I'm going to try to be a little bit more conservative. I'm going to take what might seem to be sort of a step back, and I want to consider the hardness of computing the outcome probabilities of potentially noisy random circuits. Right now, when we consider, when we go from the problem that in some sense we care about, which is sampling, to this harder problem of computing output probabilities, well, as you would expect, there's sort of pluses and minuses. Right, so as compared with sampling, I would say that experiments can't efficiently solve this problem. Right, the experiments are sampling; they're not computing outcome probabilities. But at the same time, because it's a harder task, it's possible to prove much stronger hardness results. And then, of course, in practice, many classical simulation algorithms do compute output probabilities. So we can think of these hardness results as some sort of barrier for these algorithms. Okay, so what are we going to do? So here's the agenda. I want to review the average case sharp P hardness for the near exact computation of the output probability of random circuits. I want to show that these results still hold if the circuit is noisy, but in a very particular sense, which is that you have to fix the noise model ahead of time. So it's not super strong sense, right? So, but this does work, for example, for local depolarizing noise, which is an important noise model. And then I want to talk about very new classical sort of numerical simulation algorithms for 1D noisy random circuits. Okay. So maybe it's a good time to stop and just ask anyone if there's questions with what I'm trying to do. Okay, so far so good? All right, awesome. So let's keep going. Okay, so what's the problem? The problem is this: we're given as input, a random quantum circuit, and it's distributed from the from the distribution we just described. Okay. And now the goal is to compute the output probability, which I'm just going to call P0 of C, okay, with probability 1 minus delta over C. So to be completely clear, this P0 of C quantity is just what we get if we start in the all zeros state. We apply our random circuit, we measure in the standard basis, and this is the probability of seeing all zeros again. And so that's what I mean by P0 of C. I'll be consistent about that throughout the entire talk. Okay, so to prove this is sharp P hard, we give what we call a worst case to average case reduction, right? And roughly speaking, what it says is sort of described in this picture, which is a little bit misleading. This worst case circuit here could really be an arbitrary circuit anywhere in the space of quantum circuits. But the structure of the argument goes something like this. It says, suppose we have an algorithm that works to correctly simulate, to compute the output probability of a sufficiently large fraction of the space of quantum circuits. Okay, then we can use that ability to compute the output probability of a worst case or arbitrary quantum circuit. Right, so this is usually seen as sort of a proof by contradiction. We usually understand the worst case hardness pretty well, and we usually think of that as being hard, like sharp P hard, so no algorithm could solve this. And then we say, well, if it was the case that the average case was easy, then also the worst case would be easy, and so that's a contradiction. That's sort of how this argument is going to work. Okay, and it's going to build on a famous result of Dick Lipton on the average case hardness of computing the permanent of a matrix. Okay. Okay, great. So let me now go through Dick Lipton's argument. There's a number of reasons I want to do this. One, because it's one of my favorite proofs. It's just a beautiful proof. I think everyone should know this. It's very simple, but very clever. The second thing, which is maybe deeper, is that I think we've been discovering as a community now many sort of mathematical similarities between the permanent of a matrix and the output probability of a quantum circuit. These are somehow, I think at a high level at least, similar mathematical quantities. And I'm going to make many sort of ties to the between these two quantities. All right, so so first of all, the permanent of an n by n matrix is sharp P hard in the worst case. This is the same worst case complexity as computing the output probability of a quantum circuit. Right? So that's the first similarity. Now, the permanent has a very simple, algebraic property, which is that we can think of it as a degree n polynomial on n squared variables, where the n squared variables are the matrix entries. Okay, so that's easy to see from the formulation of the permanent. Okay. Now, here's the setting that we're working in, right? Someone tells us that we need to compute the permanent of a worst case matrix, right? Well, we don't know how to do that, but we do have an average case algorithm at our disposal by assumption. And what that average case algorithm is kind of a faulty algorithm, O, that works to correctly compute most permanents over the finite field. Okay, we're going to work on the finite field setting where P is sufficiently large. Right, so this is what O does. It agrees with the permanent on most random matrices. Okay, but we have no idea what happens when it doesn't agree. To get it completely wrong, and nor do we know from the end user perspective using this faulty algorithm O, we don't know when it gets it right or wrong. All we know is that it works with a sufficiently high probability. Okay, and so the question is, how can we use this average case algorithm, this faulty algorithm, to simulate our worst case quantum circuit? Right, so that's what Lipton is trying to do. And so here's how he does it. It's it's an elegant argument. He's going to choose n+1 fixed non-zero points in our finite field. So let's say P, the size of the finite field, is at least n+1, right? So let's call it T1, T2 through Tn plus 1. And then we're going to choose a uniformly random matrix, okay, over our field. We'll call that matrix R. Now we're going to consider the line A of t, which is x plus t times r. Okay, so x is fixed. That's our worst case matrix. And now we're doing a random shift by r, right? There's sort of two observations about this line, and then once you see that, the proof sort of works out for itself. So it's very nice. The first observation I call the marginal property, which is that for each I, A of t sub I is a random matrix over the finite field. Again, that's sort of self-evident, because what we're doing here with A of t is we're taking this fixed matrix X and we're shifting by something random, right? So at least from the perspective of a finite field, we get a uniform or a random matrix. We sort of lose where we started, the fact that we have X there, right? And then the second property is that there's a univariate polynomial structure here. And this is going to sort of allow us to recover the permanent of the worst case matrix using the permanent of a whole bunch of random matrices, right? And that's just that the permanent of A of t is a degree n polynomial in this single variable t, okay? That's not surprising either. That comes from the algebraic property of the permanent, right? The fact that the permanent is a degree n polynomial in n squared variables. Right, so now this is a degree n polynomial in the single variable t. Okay, okay, but the point is this: by the fundamental theorem of algebra, right, we have a degree n polynomial. We have n plus 1 points, and so these evaluation points uniquely define this degree n polynomial. So it's possible to use sort of error correction, or you can even think about it as polynomial interpolation techniques, to sort of take these n plus 1 evaluations of our degree n polynomial, recover the coefficients of the polynomial, and then evaluate the polynomial at t equals 0. And because when a of 0 is equal to x, this is our permanent of our worst case matrix. Okay, so very nice argument. It's a little bit slick. So any sort of questions here? Okay, are we good? Let's see. We do have some I've heard it. All right, we'll talk about some of these questions later from the Q&A. Okay, great. So now what we're trying to do is adapt this proof to the random quantum circuit setting. Okay. So the first thing we notice, so this is another similarity between the permanent and the output probability of a quantum circuit, which is that much like the permanent of a matrix X, the output probability of a random quantum circuit, or for that matter, quantum circuits in general, have a sort of low degree or moderate degree polynomial structure. Okay, so how are we going to see this? Let's consider taking a circuit, an arbitrary circuit, and breaking it apart into its gates. Okay, so Cm minus 1 through C1. And those are the gates of the circuit. Maybe they're 2 qubit gates, it doesn't matter. Well, I'm going to claim that polynomial structure comes from the Feynman path integral, okay? Which allows us to write the output amplitude of this quantum circuit as this giant sum over paths. Okay, these are values of these y variables. And there's an exponential number of paths, but the important point is that the value of each path is the product of m gate entries. Okay, that's what the Feynman path integral allows us to do. We're just inserting sort of identity gates really here. That's really what we're doing. And the thing to notice right away is that this is very similar in some ways to the expression of the permanent I just said. This is a polynomial of degree m in the gate entries of the circuit, right, where m is the size of the circuit, okay? And so in particular, by the Born rule, the output probability of the circuit, this P0 of C, is a polynomial of degree 2 times m, right? It's not surprising. We're just squaring the amplitude, okay? Great. So we now have polynomial structure. So let's try to take this structure and just blindly copy Lipton's proof. Well, anytime you do this, almost every time you do this in math, it doesn't end up working. So we're going to need to do something smarter than this. But let's see what we would do. So again, let's just recall what the goal is. We want to compute the output probability of a worst case circuit C. But we only have the ability to compute the output probabilities for most circuits. We only have an average case faulty algorithm that does this for most random circuits. So let's recall what Lipton did. Well, he wanted to compute the permanent of a matrix X, and he chose a random matrix R, and then considered this line X plus T times R, right? The problem is, and sort of obvious, we can't just perturb quantum gates in a random linear direction. It's because unitary matrices aren't linear. You can't take a unitary C, which is maybe your worst case unitary, take a random unitary D, and then take C plus T times D and expect that to be a unitary. That's obviously not the case. So we can't do that. Okay, so that fails. So what we need is sort of a new approach to scrambling the gates of a fixed quantum circuit, like our worst case quantum circuit C. Okay, so here's a new method. This method will also not quite work, but it gets us a little closer to what we want. Let's consider choosing and then fixing M Haar random gates, which each one is say 2 qubits, and I call them HI. So there's one Haar random gate chosen independently per ideal gate in our circuit. Okay. So now what we're going to do is consider a new circuit, which I call C prime. Okay, so that each gate in this sort of scrambled circuit, C prime sub I, is defined to be the ith gate of our ideal circuit times HI, this totally Haar random gate. And notice that right away, by the invariance property of the Haar measure, each gate in C prime is completely random, right? It's Haar random. And so this is, of course, good because this is the analog of Lipton's marginal property, right? That, we've sort of forgotten where we start with, where we started. We're completely random. But the problem is, Lipton didn't just scramble things. He also had this sort of nice univariate polynomial structure that connected the worst case circuit C with the new circuit, with the scrambled circuit C prime. And we don't have that here, okay? So that's not going to work. But it's getting us closer. And what we need is what I'm going to call correlating a whole bunch of random circuits via quantumness. So what do I mean by that? Well, again, we're trying to find the analog to Lipton's univariate polynomial structure. And so the main idea is we're going to do this sort of uniquely quantum thing, which I think is pretty cool. So we can take quantumly, it makes sense to implement a tiny fraction of HI inverse, or a tiny fraction of a unitary matrix. In particular, we're going to apply that to the inverse of these random gates. So here's what I mean. Let's consider a new way of scrambling our worst case circuit C. Each scrambled gate, C prime sub I, is going to be Ci, that's the ideal gate of the ith circuit C, times Hi. Now, as before, we're completely scrambled, but now we're going to implement a tiny fraction, like a theta fraction, of the inverse of this random gate Hi. Okay, and now I'm going to claim that this sort of has a Lipton-like structure to it. So what do I mean by this? Well, what I mean is that if theta is equal to 1, okay, then the corresponding circuit, right, is exactly equal to the worst case circuit. I hope that's clear. That's because we're just inverting the HI, right? But if theta is really tiny, let's say it's inverse polynomial, right, in the system size, then each gate is really close to Haar random, right? Is it clear why? Because essentially what you're doing is taking your worst case gate, you're scrambling it, and then you're doing almost nothing, okay? Okay, so now what you can hope to do is the following, which is very Lipton-like. Again, you can hope to take several non-zero but tiny theta. For each one of those theta, you get a different random but correlated circuit. Okay, and you take a whole bunch of different theta. For each theta, a whole bunch of for each theta you have a different sort of scrambled circuit, and then you can hope to apply some sort of polynomial interpolation at the end of the day to recover the output probability of the worst case circuit. Okay, so that's an idea. It turns out not to work, and the reason is because e to the minus I hi theta is not a polynomial in theta. Okay, so what are we going to do? Well, the solution we propose is to take a fixed truncation of the Taylor series for e to the minus I hi theta. Okay, and now, so in other words, what do I mean? Let's be really careful. So what I mean is each gate in the scrambled circuit now, and we're changing it slightly, right? It's now going to be Ci times Hi. Again, that's completely scrambled. Now, instead of applying the theta power of the inverse of Hi, we're going to consider the truncated Taylor series for this gate. Okay, so what did we gain here? Well, now, each gate entry can be seen to be a polynomial in theta. That's because the Taylor series itself is a polynomial in theta, right? And then by the Feynman path integral, what we're essentially doing is, we can write the output probability of this new truncated circuit, C prime, as a big sum over products of these gate entries, right? And that preserves the polynomial structure as well, right? So the output probability of the truncated circuit ends up being a polynomial in theta, okay, of degree that's somehow related to the size of the circuit, right?
But C prime is not unitary anymore?
Yes, C prime is not quite unitary. More about this coming, but absolutely, thank you. Okay, but now we can hope to take a whole bunch of thetas, small thetas, right? Each one of them looks, for each one of them we have a scrambled circuit, C sub theta, right? Those C sub thetas look very close to random, right? And so we can hope to use our faulty algorithm that works with high probability for a random circuit to compute the output probabilities of those random looking circuits, C theta, okay? And then we can hope to interpolate, find this polynomial Q in theta, and output the value of theta at theta equal 1, which is the output probability of our worst case circuit C, okay? So yes, I agree this is non-unitary. We'll talk about that. That's sort of a very interesting issue here. But any other questions about what we're doing? Okay, good. So let's keep going. Okay, when we try to understand this construction, we see that there are sort of a variety of sort of interesting details, okay, sort of subtleties. The first one, which is by far the most important one, is that, and this is, by the way, not just in our construction, but in any of these quantum supremacy constructions, is that polynomial interpolation is extremely sensitive to additive error. Right? So what I mean by this is that, if instead of exactly computing the output probability for these C theta, these scrambled circuits, we get some approximation, okay? Then when we interpolate, in principle, our interpolated worst case point could be way off. Okay, so as a consequence of the fact that polynomial interpolation is sort of not well conditioned or very sensitive to additive error, this severely constrains the robustness of this average case argument. Right. So if you look at my sort of interval picture here, if this is the output probability of the true quantum circuit, C, that's the random circuit, that's what we want to argue is hard. And this is the output probability of C prime, which is slightly non-unitary, but in general, extremely close to P0 of C, right? Then it turns out that we can only show hardness to compute any point in this tiny, tiny red interval of width 2 to the minus n cubed, okay? And then it turns out, so far we've only been talking about the hardness of computing, but it turns out that if we're really interested in the hardness of sampling, it suffices to show that it's, so if you want to prove hardness of sampling, it suffices to show that computing any point on this much wider interval of length 2 to the minus n over poly, right, is sharp P hard to compute. So I guess what I want to say is that what we've done so far is we've shown that there's a little bit of robustness around this truncated point, okay? But it sort of falls exponentially short of what we would need to go from the hardness of computing to the hardness of sampling, okay? Let's see, maybe I should stop for, there are some questions, so let's see. Let's see. Okay, yeah, I think I'm going to keep going. Okay, so there may be other ways of doing this. The second point, which has already been brought up, is that this truncated circuit C prime is ever so slightly non-unitary. Okay, it's non-unitary, because we're taking a unitary matrix, a unitary gate, and we're truncating its Taylor series. Okay, it's extremely close to the outcome probability of our circuit because the Taylor series very well approximates the actual unitary, but it's not unitary. And so how do we motivate this, right? How do we motivate that our result does not, gives us something that's not quite unitary? Well, what we show, and this is actually the technical result in our paper, and one of the technical results, we show with respect to this hardness of sampling level of approximation, the truncations don't matter. So what I mean is this, and this is actually a formal theorem in the paper, is that if someone were to show that it's hard to output any point in this wider interval of width 2 to the minus n over poly, then in some ways it doesn't matter where the center of that interval is. If it's centered around the actual output probability, P0 of C, or if it's really, really close to it. Essentially because we didn't just choose this C prime arbitrarily, it's extremely close to the output probability, okay? So we can actually make this formal. We show that, in other words, outputting an additive approximation of 2 to the n over poly, that's this hardness of sampling level, right, is hard with respect to the original circuit C, if and only if it's hard to compute the truncated circuit to that same level of accuracy. Okay, so I won't prove that, but the idea with this is just that we didn't construct this C prime completely arbitrarily. It's very close to the original circuit C, and we did this purposely to get a result like this that said, look, if you care about hardness of sampling, it doesn't matter if you're talking about the truncation of the unitary. Good. Let's see, any questions about that? Okay, it looks like I'm good, so I'm going to keep going. In recent follow-up work, hardness has been shown around the original output probability. So this is a nice result. So in particular, we do know after this sort of follow-up work, which uses similar but slightly different techniques, that computing the output probability of a random quantum circuit C itself is sharp P hard, but within this same tiny precision. Okay, so in other words, if you compare the interval picture here to the interval picture from the last slide, the only difference is that the red interval moved a little bit. Okay, and now it's centered around the original output probability. Okay, but this is very nice work. To do this, Ramis gives a new method to interpolate between the worst case and random circuit using what he calls the Cayley path, which stays unitary throughout the entire path. So essentially, it's a very similar style argument, but he changes the way he interpolates between the random unitary and the worst case unitary, and he does so in a way that stays unitary, and so he's actually able to argue about the output probability of the original circuit. Okay. Okay, great. Let's see. I can stop to pause, or we can keep going. It's up to you. I can pause a little. Okay, great. Let me keep going. Okay, so so far we've really only talked about noise in terms of sort of imprecision of the algorithm. Okay, but that's sort of not all we might hope for, right? So let me ask another question, which is that is it hard to nearly exactly compute noisy circuit probabilities, right? And so when we do this, we sort of have a fact that seems like it might be a hard and fast barrier for us, right? Which is that, for many natural noise models, not all of them, but for many of them, the output distribution of an uncorrected noisy quantum circuit sort of converges rapidly to the uniform distribution, right? And that's sort of what you'd expect. Yes, sorry?
Can I ask you a quick question about if and only if? My understanding was that the proof shows a necessary condition for quantum supremacy with respect to your proof.
Yeah.
And you said if and only if. I was wondering how both ways. Do you really have both ways, or?
Yeah, we do. We do really have both ways. Mm-hmm. Yep.
So how does the other direction work? The necessary condition is clear.
I don't want to get into such details right now. What I will say is that they're actually very similar proofs in both directions. And they're basically, the way the proofs work is that these distributions are constructed, the distribution over the truncated circuit that we end up getting and the ideal circuit, they're constructed in a very special way so that they're very close to each other in a number of properties. Okay, so in other words, it's just what I was saying before, that we didn't construct this truncated circuit arbitrarily. We chose it specially so that it has properties that make it very similar to the totally Haar random distribution. And so the proofs in both directions sort of use these properties. But I think I'm going to continue on if that's okay with you. Okay.
Sure, we can talk later.
Sure.
About
So
hardness the other way.
Okay, great. So I'm now considering sort of this noisy question, and I'm saying that you might think a priori that there wouldn't be any hardness at all here asymptotically, because as the system size goes to infinity, it's often the case for these uncorrected noisy quantum circuits that the distribution sort of converges rapidly, exponentially quickly, in fact, in the system size or in the depth to the uniform distribution. So how can there be hardness there? Well, there's sort of a counterpoint intuition, which has sort of become popular, I think, in the community, which is that maybe quantum hardness is still present in sort of tiny deviations from uniform, right? So in other words, there's this sort of hard quantum signal, and as the noisy quantum circuit sort of progresses and we're not correcting noise, it's sort of it gets exponentially diminished, right? But maybe it's still somehow there if we sort of are precise enough. Right? So let's try to formalize this. And I want to say that the way we formalize this will be pretty weak. Okay, it's not everything we would want, and I want to be very careful in saying this. But it's a starting point, I think, which is that let's say we fix a noise model ahead of time, and we know what that noise is. So, for example, maybe each ideal gate Ci is followed by a 2-qubit depolarizing noise with a certain depolarizing parameter. Okay, so here's the depolarizing channel. Okay, and that another way of saying that is we can kind of think about choosing a noisy random circuit in the following way, right? We first pick an ideal random circuit from the random circuit distribution, okay, and then the environment, or something that's sort of not up to us, chooses these M noise operators from a distribution that's specified by the channel. So for us, these are this is M 2-qubit unitary operators or polymatrices, because we're talking about the depolarizing channel, right? And then at the end of the day, we should think of getting a sample from the output distribution of this sort of combined circuit, this n.c, where dot is just gate-wise multiplication, right? Without ever learning what the noise operators are, right? So that's sort of the model I have in mind. And one thing that's really nice about this is you can see by linearity that you can write the output probability of the noisy quantum circuit as an expectation over the noise operators of the output probability of this circuit, C dot M, right? Excuse me, N dot C, right? And then what's really nice about this, furthermore, is that this can be written, this expectation can be written as a weighted sum of Feynman path integrals. Right? So I'm just writing out what this expectation is. And the key point is that this is still a polynomial of degree 2m in the ideal gate entries. So, we've added terms to this Feynman path integral, or rather to this sum, but it still has the property that we cared about. Okay. So by the same arguments as before, we actually do have a worst to average case reduction for computing the output probability of this noisy quantum circuit to within tiny, tiny tolerance, like 2 to the minus n cubed. Okay, but let me also say that before we even get to the point, and that we can also establish worst case hardness here, in this context, I almost feel like this tiny precision that we're getting is sort of more justified, because we know at the same time for constant rate depolarizing noise that the error that the distribution is converging exponentially to the uniform distribution. So I think it sort of makes sense that we would require super tiny precision. Okay, because obviously the uniform distribution is not hard. Even I can compute an output probability of the uniform distribution on n qubits, right? Okay, great. But all we've shown so far is, if we can compute this quantity for a random circuit C, we can also compute this for a worst case C. That's all we've done, right? So there's sort of an interesting question then, which is, well, how hard is the worst case circuit, right? In other words, is it hard to compute the output probability of a noisy quantum circuit, n.c, if we average over the noise, but the worst case circuit is fixed? Okay. And what's really nice is actually sort of one of the only times in my life where I sort of had this question and then it's already been solved, essentially. So it turns out that Fuji, writing in 2016, had already essentially solved this question. And what he shows is that this is sharp p hard, this computing the outcome probability of a worst case noisy quantum circuit, if it's possible to error detect. Okay, so in other words, if the gate error rate, the depolarization parameter Q, is below a constant error detection threshold. Okay, so this is sort of a nice result. It's a simple but nice argument, and it will be let me try to tell you how this works. The proof technique will be familiar to anyone who has seen prior quantum supremacy arguments, which is that sort of suffices to be able to show the universality of noisy quantum circuits under post-selection, right? So that suffices to show that this output probability is hard. And what Fuji says is the following. I'm paraphrasing, of course, wildly, but roughly this is the idea. Well, let's suppose we have this noisy circuit, but we have both the ability to post-select and the ability to detect errors. Right? Well, then why don't we combine these two sort of superpowers and post-select on the syndrome measurement outcomes corresponding to no error occurring, right? So if you do this, then it's clear that you get, if you can know for sure that you didn't have any error, and you can post-select on, exponentially improbable measurement outcomes, then it's actually clear in this setting that you can get hardness. And that finishes the proof. It's sort of a two-sentence summary of what he does. But the interesting thing here is that you don't need error correction, right? It suffices to get error detection, which could be a lower detection threshold, which could be a lower threshold. Right, but what I'll say is there is a caveat, which I think is very interesting to try to ask if this is necessary or not, which is that this requires a huge overhead in number of qubits to error detect nearly perfectly. So if we really wanted to implement his scheme, we would need an additional overhead of a polynomial number of qubits, and it's to error detect really perfectly. So that what you need is, at the end of the day, if you see no errors, if your syndrome measurements indicate that you have no errors, that the output probability of the error detected circuit is like exponentially close to the ideal circuit, which is very demanding. Okay. But what I want to say is that nonetheless, as a consequence of combining these two results, I think it's pretty nice that we can say computing the output probabilities of noisy random quantum circuits is actually classically hard as long as the noise per gate is below this error detection threshold. That's what we get when we combine these two results. And I think there's a lot of really interesting work to do here to ask if this is somehow optimal in some sense, or if we can do even better than this, at some lower threshold. Okay. Okay, great. So should I take questions here? We're okay.
So Google should be testing whether their noise is below the error detection threshold in some sense.
Yeah, right? I think
good target, even though it's not useful, is to
yes.
try to implement error detection and see if it helps in mitigating errors. Is a good thing.
Yeah, that's what I'm trying. I mean, that's a message. And of course, there are a lot of drawbacks of these results. They require overhead and so on. It's sort of still, I would say, in a theoretical, these are theoretical results, but that is sort of a high level message that we're trying to say at some pretty high level. Okay. Okay. Great. And I think another thing that's really interesting about this, like I said before, is purely theoretical. It's that, this sort of might tell you why there's a barrier in extending these arguments and making these average case results more robust, right? Because we know that at some point this quantity is well approximated by the uniform distribution, right? And so this is sort of saying that we can't make, there's not, at least in this setting, there's not going to be just a sort of turnkey way of making these worst to average case results more robust. Okay, because we know that the robustness is false at a certain point because the uniform distribution is easy to output. And so that I think is an interesting message here too that has nothing whatsoever to do with experiment. Okay, great. So, okay, great. So I have a little bit of time. I want to tell you just briefly about some new results that I'm pretty excited about. And so I'm a complexity theorist, so of course I'm interested in hardness, but we're also really interested in easiness results. And these are, of course, sort of flip sides of the same coin. But in particular, we're inspired by many recent classical simulation results for restricted classes of quantum circuits. And you just heard one of the ones that we were really excited about, this result of Knapp and Aram-Harrow and so on. We're going to focus on kind of a related but different topic, okay? Which is we're going to consider a very simplified setting of random circuits, not really applicable, I think, to quantum supremacy directly, which is 1D random circuits with Haar-random 2-qubit gates and local depolarizing noise, okay? So it's very similar to what I was talking about, except we're talking about 1D setting instead of 2D setting, okay? Which of course makes a big difference, and I want to be clear that what I'm about to say is not directly relevant to the Google experiment, except maybe by some very loose analogy, okay? Now, but I want to recall something, which if you have constant rate of depolarizing noise, the output distribution of the random circuit is eventually going to converge to uniform, okay? Now, before we were talking about, well, at least in the 2D setting, we can sort of look at asymptotic behavior and ask if there's still this tiny quantum signal that's surviving, even though it's exponentially suppressed. Here, I want to ask sort of a different question. This is a more pragmatic question, which is the following. Oops. Question. Okay, a more pragmatic question, which is for a given fixed error rate, what's the hardest depth to implement or system size to implement, and where do quantum correlations peak? Okay, so this is not an asymptotic question. This is a non-asymptotic question. It's a vague question as currently formalized, but it's important, right? In other words, what really is, if you tell me that the error rate is something, what is the right depth to implement or system size to implement? And so, as you might imagine, we have to do this numerically. And when we do this, we don't fully understand these results theoretically, but I think we have some interesting plots I'd like to show you. Let me tell you a little bit more first about these results. We're going to consider what we call the MPO entanglement entropy of the resulting mixed state after we apply this noisy circuit. I'm not going to define very carefully what this measure is, this entanglement entropy is. Some people probably know it already. It's called different things in the literature. Sometimes it's called, I think, operator entanglement or something like this. The point is it's a measure of quantum correlations between two disjoint subsets of qubits, and it reduces to the standard entanglement entropy measure in the special case of pure states, which is sort of nice. Furthermore, the reason we chose this quantity is because it turns out to determine the cost of classical MPO simulation. Okay, so it turns out it sort of gives an upper bound on the classical complexity of computing the output probability of the circuit. We can do this in time that scales exponentially in, it turns out, the maximum MPO entanglement entropy, or the maximum here is taken over the system over the subsystem length. Okay, but essentially this is because this entropy measure can be used to bound the required bond dimension chi needed to accurately describe a mixed state, talking about our sort of truncations, and so essentially these MPO techniques, they run in time polynomial in n and chi, and so in general we have to think of them as running exponentially in this entanglement measure. Okay, so that's sort of the only thing I want to talk about with regards to this measure. We sort of wrote a whole bunch about it, and you can read more in our paper. But I want to show you some interesting plots, which I think are very fun to look at. So we have 3 of them here, and there's many more in our paper. But what we're doing is each plot has a different fixed 2-qubit error rate p. So otherwise, they're graphing the same information, but the depolarization parameter, the noise strength, is different and is fixed in each graph. Okay, and then in each graph, we're graphing the circuit depth on the x-axis and this MPO entanglement entropy measure on the y-axis. Okay, some measure of quantum correlations that again gives us an algorithm that runs exponentially in that time. And then what we're doing is each color here, each line corresponds to a different system size, okay, which goes from n = 4 to n = 18. And each point in the plot is averaged over 24 different random circuits. Okay, so what we see is the following, which I think is not super surprising. For each error rate, okay, so each fixed graph, there's sort of a peak depth at which correlations are maximized. Okay, so you can see that, you know, for example, here at the error rate 0.15, you can see that at around depth 5 for all the system sizes, they're sort of simultaneously maximized their entanglement measure. And what's more, which I think we found sort of interesting, I don't quite understand this theoretically yet, is it seems like at this peak depth, after a sufficiently large system size, you know, adding more qubits doesn't actually change this entanglement entropy measure, right? So there really is a sense in which, you know, after you fix the gate rate, it doesn't seem like it helps you to increase your system size, right? And, you know, you can see this very clearly, for example, in this plot here, if you can see my mouse, you know, when we go from system size 4 to system size 6, we're sort of slightly increasing our entropy measure. But then, you know, after a certain point, you know, after size like around 8, you know, we're really not seeing any increase in this particular measure, right? And we see this in each and every one of these plots, okay, about the same thing. Right? And again, that I don't actually have a theoretical explanation for that. I think the fact that the shape of the curve is like this, I think that's clear. I mean, essentially what's happening is, you know, when you have uncorrected noise, you're converging to you know, a maximally mixed state that's going to be a uniform distribution. It doesn't have the quantum correlations that this measure is measuring, but the fact that it's sort of, you know, there's like for each gate error rate, there seems to be like a peak size, and after that, you're not gaining. That's something that I think is sort of interesting, and I don't understand that very well theoretically yet. Okay, so from the perspective of this particular algorithm, once we fix the noise rate, the hardness seems to saturate at a fixed system size. Okay, let's see it one more time, and then I'll wrap up. So to see the saturation behavior more directly, we can plot the number of qubits versus this entanglement entropy measure at the optimal depth. Okay, so remember, for each gate error rate, we have an optimal depth. And each curve here represents a different error rate at the optimal depth for that error rate from the prior plot. And what we see pretty clearly here is that it seems like there's a maximum system size that's determined entirely by the error rate, after which we don't gain in quantum correlations according to this measure. And this is happening for each one of these gate error rates. So for example, if you look at 0.06 here, you know, it seems like we're increasing our correlations until we get to around, I don't know, 11, 12 qubits, and then we sort of flatten. Okay, and that happens for each one, for all of these gate error rates individually. The only difference is that where that peak is happening, the peak system size is different. And as you would expect, as the gate error rate gets worse, the sort of number of qubits that sort of, you know, we flatten at gets lower and lower, right? And so that's what we're seeing here. Okay, great. So let me just conclude. So numerically, we sort of observed that for noisy 1D random circuits, there's a sense in which quantum correlations peak at a particular system size. We can make use of this observation to compute the noisy output probabilities using matrix product operator methods. But on the other hand, we can prove that sort of in this very different asymptotic regime, you know, computing noisy output probabilities to very extreme precision is hard in 2D below a noise threshold. And that's combining our results with the results of Fuji. Okay, great. So let me wrap up here. And thanks to you know, many of my collaborators for a lot of useful conversations about this topic.
Great, thank you, Bill.